Well, good morning, everybody, and welcome to Ellensburg, Washington, USA, home of Central Washington University. And our speaker, this is a live look at your speaker eating lunch quickly before he speaks. That's Chris Mattinson talking to Hannah Shamloo, and Chris has been teaching all morning, scarfing down a sandwich, and then the poor guy has to give an hour-long talk to all of us. So let me move the camera just slightly and give him a little bit of privacy. And I can say hi to a number of you. And Hannah Shamloo is going to run the show this morning. Hi, everybody, and welcome. Thank you so much for tuning in live. The local time is probably 11:48 a.m. Pacific time. It's a Friday here. And this is a Friday noon talk, which means that we will begin the program 15 minutes from now, probably. If you're watching this in replay, I will put a chapter title for when our speaker, Chris Mattinson, actually starts speaking. But we have a number of department announcements and other things, plus this pre-show stuff where I'm saying hi to a bunch of you. Where are you viewing from today? Can I say hi to a number of you before I give you a sense of the room? There's a lot of good energy in the room today. It's still January. How's that possible? It's like the longest month ever. Central Lake, Michigan. Natchez, Washington. That's not French, says Pat the pilot. My live chat is stuck. Now it's gone. Dorset, UK. Alberti Gary in the fog per usual. Hans is in the Netherlands. Looks like we're loud and clear. Thank you. I'm starting to like these mics, but it's not easy. Live chat is acting funky for right now. Elma, Washington. Winter Garden, California. New Plymouth, Idaho. Burlington, Washington. My live chat is flickering. Is everything okay with you? Can I ask again? Are we loud and clear? Are we crystal clear with audio and video here? I almost don't want to see what you're typing, but things are a little bit pyrotechnic in my live chat. It's probably my iPad. We're good? New Jersey, Parkersfield, Kansas. 5x5. Thank you for all that. Whidbey Island, Washington. Okay, well, enough of me. You get a chance to see me regularly. I'll see many of you tomorrow morning, Saturday morning, at 8 a.m. Pacific time. At least I know what the title is. It's going to be Big Red Plutons. Saturday morning, 8 a.m. Pacific. I think that's session S of the Cascades A to Z. So we'll see you all then. But you're tuned in to listen to this lecture, and I'm sure that it's a good one. Thank you for joining us. We'll start in a few minutes. You know, you could be here. You could be a geology major at CWU sitting right here. So you're just going to give me a head nod, or when do you want me to put that photo on the screen?
Basically, when I finish his professional trajectory, I'll say something personal. That's when you put it up.
Gigi. Gigi. Would you like to say hi to everybody?
Hello, YouTube. Top of the morning. Actually, no. Good afternoon.
The sun's already gone down in Ireland, I suppose. When did you start teaching this morning?
What?
When did you start teaching this morning?
This morning, I didn't have class this morning.
Oh, you did?
Yeah, we meet Monday through Thursday.
Oh, you're just a regular lunch guy. That's all. I made that part up. Chris didn't teach this morning. All right.
your language. This is a family-friendly film.
You mean America.
Keep going. Keep going.
Yeah, what are you talking about now?
Hayden, you can't say that about. You can't say that anymore.
Oh, yes.
You're so excited for your interview?
Red's Fly Shop. I don't know what I'm interviewing for, but I'm interviewing for something, and I'm going to be in the canyon, which will be cool.
Good. That's today?
Yep, right after this.
Good luck. Davey, looking at the live chat?
Yep, always.
Why don't you type something in? Let's see what kind of delay we
Want me
have.
to pull up something?
Or I guess, how would we know?
I don't think I have a channel, so I would have to look up.
You don't have a YouTube channel?
No, I haven't actually made an account.
Oh, so it doesn't let you type in?
I don't think so. Yeah, I gotta create a channel to join the chat.
Oh, what? That's how they get you. Oh, I didn't know that. Morning. Hi. I'm Nick.
Catch me on it.
Nice to meet you.
Nice to meet you too.
Do you live in the building here?
No. Well, no, I mean, I just have some classes in this building.
Okay.
Yeah.
Are you majoring in something else? Are you a professor here?
I'm just taking some post-bac classes.
Oh, wonderful.
Yeah, that's all.
In geology.
Yes. Yeah.
Have we visited before?
No.
Okay.
But I know who you are.
Okay.
Of course, yeah.
Well,
So,
let's visit a little bit sometime.
yeah.
Yeah.
Well, thank you for saying hi.
Sure. You guys? All right, where are you going to sit, man? This is a big decision.
This is the biggest decision you have to make.
Right.
Where?
It could backfire on you.
It could.
I don't know.
I don't know either. My crew, the 210 crew's up front.
Okay.
There's a lot of pressure there being up front. So maybe I'll hang back a couple. I don't know.
Whatever it is, you'll make the right choice. I believe in you.
I appreciate it.
Yes.
Howdy, Nick. How's it going?
Good, thanks. Same.
Gotcha. Okay, cool. Work on it a little bit, just to be like, and at the end, like, oh, you were in that class.
Hi. Morning. Okay, everybody, we're going to test Chris's mic here. He's eating an apple, so you're going to be able to. We're going to test the crispness of the microphone as he bites into a crisp apple. Okay, we're really going to test this microphone, Chris, because we're going to hear the crunch of the Jana Gold. Please be careful with these wires. All right, so this viewers, I'm going to put this mic on Chris, and you're going to let me know if it's Chris 5x5 as he talks to me a little bit. I'll come in right like, I'm even going to come up here, Chris, if you're okay with that.
Sure.
Perfect, right?
Yeah.
there. Okay, so I guess, let me get my iPad, Chris.
Okay.
All right, what are we talking about today, Chris?
Well, we're talking about metamorphic petrology, Nick.
Oh, I think I saw that one coming.
Uh-huh.
And it's a mixture of just this past summer or multiple years now
It's
of
multiple
work?
years. It'll be a different style of talk.
Good.
So it'll be a little, the beginning part I'll do a little similar to what Tim did, a little bit about my background and
Good.
my trajectory ending up doing what I do, and more a little bit of a few different facets as opposed to a deep dive into one thing.
I love it. I love it. Well, it looks like you're loud and clear. You're 5x5, so
Okay.
I think we're good.
Nick, I don't know if you're able to mute me so I can finish my eating my
Just
lunch.
go ahead.
Just
Just
go
go
ahead?
ahead, yeah.
Okay, well,
Did you take this out of full screen?
Oops. Sure did.
You son of a gun.
You son of a- oh, wait.
We got to go full. Yes, start swearing.
Start swearing. Give the people what they want.
Okay, I'm going to turn this on. Are you ready to go?
Yeah, I'm ready.
I'm just going to make sure that my voice is going through that speaker, and then you're the gal. Okay?
Are you done with your lunch?
Still got 3 minutes. I think it'll be all right.
My phone says 1 minute. You're good though. Eat.
Testing, testing. Testing. Megan Miller, can you hear me in the back? Andrew Sadowski, can you hear in the back? You can? Good. Okay. I think we're up and running. Thank you, everybody, for coming. Nice full room here. Hannah Shamloo, take it away.
All right, hi everyone. Welcome to another Friday seminar series. We love seeing everyone in here. Okay, a couple announcements before we get going to our talk today. So if your name is Tim Melbourne, please raise your hand. Tim, thank you for the awesome talk last week. Also, if you are in 304 or 504, Tim's your man. Make sure you're checking in with him so that your attendance is accounted for. Another announcement from Tim is if you're in Geology 487, who in this room is in 487? Couple of you, you're going to be meeting in room 105 today. Did I get that right, Tim? Okay. Okay. No, yeah, just next door. Okay, if your name is Bree McInnes, raise your hand. Hi, Bree. If you got, you're like, why me? If you have not signed a release form with Bree to be off or on camera, please go see Bree. This section of the room, you will not be on camera. You still have a form. This section of the room, you are on camera. You have a form. Okay, so see Bree if you haven't done that yet. The schedule for the remaining talks of this quarter, we have Sean Scott from Pacific Northwest National Lab. That's going to be a good one. We've had 2 people from PNNL give talks here, and they're always really interesting. Sean is also a liaison for student internships at PNNL. So if you're a student in the room, you should stick around and talk to Sean because he has opportunities for undergrads and grads at a national lab. Then we have Ann Egger, supporting equitable and effective teaching in undergraduate STEM. And then we have Paul Winberry, our own, using geophysics to better constrain Antarctica's future sea level contributions. Okay? Okay, but I'm going to get on to our speaker if you want to go ahead. Okay, it is my great pleasure to introduce our very own Dr. Chris Mattinson. Chris is a California kid through and through. He is from Goleta, California. He did his bachelor's degree at University of California, Santa Barbara, or UCSB. He then went on to Stanford to get a PhD and then stuck around at Stanford for a postdoc, lecturer, and research associate. Pretty impressive. And then he started here at Central Washington University in 2008, and he's been here ever since. Chris is very much a staple in our department. He has been a wonderful mentor to me. He's very dedicated to his students, and I think that it's a mutually exclusive feeling, Chris. Yeah, so Halloween last year, Chris's students in his petrography class all dressed up as one of their favorite geologists, who happens to be Chris Mattinson. So I think it's very clear that he's well loved here. Okay, thank you, and please help me welcome Dr. Chris Mattinson.
All right, so we had that surprise photo, so now we have to take a moment to get set up with Chris's talk. But nice job with the outfits and everything. So, Chris, please take it away.
Okay, well, thank you, everyone, for the opportunity to talk here.
Yep, thank you.
All right, so I'm talking about my research. This is going to be a kind of a different style of talk. So instead of doing a deep dive into a specific project all the way through and the methods and the conclusions, it's going to be a bit more about what do I do, how did I get into it, what was my career path, and giving you a few facets of some of the different applications of my science. So I hope that will be of interest. So here's a photo, here, my field area in Western China. That's part of what I'll be talking about today. So we're going to be connecting continental growth, building the continents, hazards, and critical mineral resources, and how that's all connected to metamorphic processes, which is my specialty. So first off, not very much is able to happen without money. And so first off, I want to thank the multiple organizations that have made this possible. So obviously big time funding coming from National Science Foundation, Washington Geological Survey, and USGS, and also a lot of student funding coming from both Central Washington University, Geological Society of America, and also had one student who got some support through Society of Economic Geologists. And Yakima Rock Club has also been a consistent supporter of our students. So this really makes a huge difference, both on the supporting the research expenses side and supporting the students side. So a little bit of a roadmap. So what is metamorphic petrology? Why am I passionate about it? Is where we're going to start. And then my nonlinear path as a geologist to getting what I do. And then we're going to look at 3 different facets of my research. And as I was putting this together, I realized they have a common element, so I'm going to call this following the fluids. And this is going to be our little mascot guiding our way here. So my students from Rocks and Minerals will recognize our little character here. So before we get into that, though, I just wanted to give you a little appetizer of why should we even care about the Earth's deeper interior? And so this is a thermomechanical model from Dr. Elena Sizova and her collaborators. Just gives us a little bit of an idea of all the cool, amazing, complex stuff that's going on down in Earth's deep interior, and why we might actually care about understanding those. And we will be looking at a few different facets of that along the way. So this is a model for continental collision here that I think is pretty cool. And again, models are not the same as reality, but they give us really key insights for questions or problems that we can then address. So great, lots to see. But how do we do it? So metamorphic processes, pretty much by definition, are not happening up in our everyday surface world. So you can't just pull up a lawn chair and watch. So what do? Okay, hint, not this way. So what do I do in my research? So there's a lot of different facets to how you can study the Earth's interior. I come from the approach of studying natural samples and using them as flight data recorders. I realized after I put this together and then hearing the horrible news of that plane crash just a few days ago, I hope nobody takes this the wrong way, but I think of rocks as nature's flight data recorder. And fortunately for everything that we are going to talk about today, it was millions of years ago. No humans were even in existence to be harmed by any of these geological processes. So we can enjoy it with a clean conscience. So strategy, a lot of what I do is when we go into the field, how do we select a sample that actually is going to be our flight data recorder? Thinking about what process we're interested in, what is going to have recorded that, and what is going to have preserved that recording, and then how can we be ingenious and creative and collaborative in figuring out that story? So this is integration, a lot of different types of observations at different spatial scales as well, which I really enjoy. So that might be the macro scale in the field, the micro scale in the laboratory with different types of analytical techniques. And so metamorphic petrology is the science of how we read that record of Earth's processes, and it's really broad because it covers really everything from the surface and near surface conditions that we feel as the rightful purview of sedimentary geology and geomorphology and other topics dealing with the Earth's surface, and the processes in the Earth's deep interior. So it really covers a broad range of things. And I really enjoy also the way it integrates and collaborates with a lot of different geological fields. So for this talk, I'll be specifically talking more about tectonics and igneous petrology, geophysics and economic geology, but there are many more. I also really enjoy the way it connects to allied sciences outside of geology. So there's been, for many, many years, a very productive collaboration between materials science and the world of petrology. So rocks, of course, are natural materials, but the physics and the chemistry underlying it are fundamentally the same. And so there's a lot of very fruitful back and forth that I find really fascinating. And so these are just a few visuals showing this. So here's some cool new tomography results on the geophysics front that, again, is providing this really amazing new data set for us to integrate. Here is a diagram down here on the lower right of a diamond anvil cell showing some of the ways that we can get experimental data. A little cartoon of the India-Asia collision. You get the idea. And what's cool about it is because we're dealing with complex rocks, we need to be highly collaborative and bring together different areas of disciplinary expertise. And you always need to know a little bit, enough to realize that there might be something to learn, and always be open-minded about something new and looking for opportunities to collaborate and make use of new data types and new techniques. It's also very international. I have met many international colleagues. That's been really exciting and wonderful part of this science, and also that it connects to so many different areas. The other thing I really love is connecting to the big picture. So for me, I always need to have that big picture tectonic connection for things to make sense, but we're also connecting the small scale. So that's why I'm so passionate about this. And so I want to share a little bit of that excitement with you today in this talk. But first, my background. So as Hannah mentioned, I grew up down in California, which is a very geologically active place. So here's a photo of the UC Santa Barbara campus, and I grew up just a few miles away from here. And so we can see the San Ynez Mountains. So these are folded and faulted and uplifted marine sediments. Behind those is a subduction complex, part of the Franciscan complex. And the campus there is sitting on an uplifted marine terrace undergoing active erosion as well. Student apartment complexes, at risk of falling into the ocean, for example. So lots of really cool things going on. I always knew I wanted a career path that would keep me connected to nature and the outdoors. And UCSB had a degree program that I thought would fit the bill. Hydrology. This was a relatively new interdisciplinary program that they had, and so I thought this would connect the things that I found really exciting and interesting about geology. So as many of you know, my dad was a geologist, so I grew up going on geology field trips and so forth and was exposed to it. And I thought, well, this would be a different application. I didn't want to do exactly the same thing as my dad. I want to do something different. So, and as I was preparing for this talk, I had a couple of my hydro textbooks sitting on my shelf, and I thought I would put those in there, and even found a sheet of notes from, evidently for an exam, for one of my hydro classes. So there were different tracks to this degree program. You could do biology, chemistry, engineering, or geology. I was in the geology track, so I was taking geology classes as part of it, and as I was going along, I found that the things that were really most exciting to me were the things that were connecting to big picture tectonics, and so I gradually started getting more and more into the solid earth side, and so I ended up adding geology, and so I did a double major. So I finished my hydrology degree as well as geology. One experience that was really formative for me was my summer field class. So this was going out there. I really enjoyed integrating and applying a broad range of geological skills and knowledge that I'd been developing. Also developed a lot of confidence to be able to deal with complex real-world problems there. It also led to my first undergraduate research experience. We were out there doing our field work in eastern central Nevada, and I happened to discover some plant fossils out there, having no idea this was actually really unusual for rocks of this age in this part of the world. Unfortunately, one of my TAs was a paleontologist and called my attention to the fact that actually this is really important. And so there was a paleobotany professor, Bruce Tiffany, who very graciously mentored me through a research project and learning valuable lessons in scientific writing, like actually proofreading and making sure what you're saying in one part of your paper is agreeing with what you say in the other part. And this led to my first publication. So going through that publication experience, And again, I'm very appreciative for Bruce for taking the patience with me and stepping me through that process. It was a really great experience. As part of my classes, learning about metamorphic petrology, I was really hooked because getting exposed to this really cutting edge science and that really integrated a broad range of things that I was interested in. And especially on the techniques side, I have a large component of my research is laboratory-based, applying laboratory techniques, but integrating that with observations in the field. And so I really loved that aspect of it. And especially, I really enjoyed that this was something that really broadens our perspective. So I think our everyday world is kind of on the human time scale and the human spatial scale. And so to have this window into a whole other world that really lets us take a big step back and see a whole new view on the Earth was really exciting to me. And there were a couple of things in particular. So there was a relatively new geology professor there, metamorphic petrologist, Brad Hacker, who exposed me to ultra-high pressure metamorphism. So that's metamorphic rocks that have gone down at least 100 kilometers depth in the Earth. That was not something people knew about until maybe about 40 years ago. And also, he was also one of the people working on connections between metamorphic reactions and earthquakes. To me, it was like, wait, what? Earthquakes happen inside the slab, not just at the boundary between the plates. And we now have the resolution to locate the earthquakes and to model where the reactions are occurring, that we can start seeing these connections. This was really exciting to me. And so I knew that was the direction that I wanted to go in. I was able to do another undergraduate research project, actually working on samples here in Washington, the Chelan Migmatite Complex. Some of you know of this, just a couple hours away from campus here. And so Brad mentored me on that. And that was really my first real introduction to the world of microanalysis, so the laboratory techniques that are a mainstay of my research now, and also thermodynamic calculations. How do we determine pressures and temperatures of samples in the Earth? And pressure is important because that's telling us depth in the Earth. So this is basically like our GPS of where we are in the Earth, reading out that record, that flight data recorder record, and again, getting more feedback on the writing and on the science, and on the importance of data quality and seeing if there's something that is a bit off there that you need to check on. And then here, Cliff Hobson, some of you know of him, very detailed feedback as well. So that was a really great experience that set me up for being able to do what I did in grad school, and then eventually moving on, coming here to Central. Okay, so that's chapter 1, right? My background. So follow the fluids, part 1. So for my PhD work, I worked in Western China. This was a really amazing cultural and language and culinary experience, as well as geological learning. It's really amazing to go somewhere else and realize not everybody does things the way we do them here, and it really gives you a broader perspective. Also amazing to see the rapid pace of change. So here's this little town of Dulan out in the middle of Qinghai province in Western China in 2001 when I first visited it. And here, during later field work, it's almost the same place, just looking the other way down that road, and you can see the rapid pace of industrialization out there. This is something that I've had a lot of students involved in over the years, and collaborators as well. So in particular, I wanted to call attention to my Chinese collaborator, Dr. Zhang Jianxin, who has been a mainstay of this work for, we've been collaborating now over 20 years, and I would not be able to do the work over there without Chinese colleagues who are there helping out. But today I'm going to mostly talk about the projects of these two students, Jake and David, as our example here. So moving beyond the techniques that I'd learned as an undergraduate, more recently getting into this more advanced thermodynamic modeling, where we can actually calculate and predict what should be the minerals and their compositions and their abundances for a specific rock sample and use that, again, to read out more detail of our flight data recorder. So this quantitative modeling. And so if we look at that just as an example for this particular sample, here's the field where the mineral chlorite could be part of the assemblage. So we can start to piece this together and build it up, and as a simple way, compare what we are observing in the rock right now and correlate that with what we see on our diagram. But we can do more than that. We can calculate what are those mineral abundances here. I'm contouring the mineral garnet, and what you'll notice is garnet grows more abundance as you increase in temperature, as you increase in pressure. You can see different relationships between pressure versus temperature of those contours in different parts of the diagram. We can also contour composition. So here we're picking the calcium component of the garnet for a couple of reasons. One is that it crosses over those volume contours at pretty high angles. So that starts to give us a way of calculating a pressure temperature path in a more detailed way. Calcium is also important because its diffusion rate is much slower than other elements in the garnet. So that means it's going to preserve its primary original growth zoning more robustly than some of the other elements do. And again, these rocks have gone through a long, complicated history, so we want to have something that is hanging on to its record. So with Jake's project, we're comparing our observed versus predicted data, coming up and building up that pressure temperature path. So what was the combination of pressure and temperature? And remember, pressure is telling us depth in the earth that caused this rock to form and have that record that it does. So eventually we can put that together, and in this case we have quite a significant part of the path, not all of it, but a significant part that is recorded. Now for this talk, an important thing is thinking about the water content. How much water is locked up in those minerals? So blue on this map here is indicating high water content. Red is low water content. So we can see as we go across that path, the rock is losing water. The minerals that contain the water locked in their mineral structure are breaking down. It's getting released. That's ultimately what is fueling our archvolcanoes here in the Cascades, so Mount St. Helens, Mount Rainier, and so forth. And also, like I mentioned, that exposure in my undergrad of that connection between earthquakes happening inside the slab, such as in our region, the 2001 Nisqually earthquake or the 1949 Olympia earthquake would both be examples of that type of earthquake. We can start thinking about that. And one thing that was really interesting about Jake's research is we took that a step further and plotted what that release rate would be. So we made some assumptions about how pressure would relate to time if we're assuming a constant subduction rate. And what we found is that that release rate of the water was very nonlinear. It was pretty much some amount of fluid being released all the way along the path, but it was higher in certain parts of the path than others. And there were also major spikes correlating to the end of the stability of certain hydrous minerals. So, of course, this prompts the question, is that maybe more favorable for triggering earthquakes if there's more fluid volume being generated at certain parts of that path than others? So, related to that, I went to a conference a number of years ago, and there's a geologist, Håkan Osterheim, who has worked for many years looking at that record of earthquakes in high-pressure rocks, and he really made the point that we know these rocks must have experienced a huge number of earthquakes over their history. And it should be on us to think about how is that record being recorded, where is it being preserved, how do we read it out? And so that really got me thinking about looking with some fresh eyes at some data I had collected some time before. So on this diagram, we have an X-ray map showing compositional zoning of an eclogite, those kind of mostly reddish things with the green rims. Those are garnets, so we can see they are more iron-rich, which is red in the core, and more magnesium-rich, which is green out in the rim. And I've highlighted a couple of them. I've labeled them A and B. And on the right-hand side, I put my cartoony interpretation of what's going on. We have these different compositional zones we can recognize. But in garnet B, it appears that those interior zones have been fractured and fragmented and overprinted. And so one possibility is that represents some evidence for seismic activity in this sample. So My student David really enhanced our pressure temperature path calculation approach compared to what we originally did with Jake's project. And so that's shown here, a much more detailed path. And so I just highlighted a few different stages along this process. So our interpretation then is that we're starting out growing our garnets here. We're seeing that record start at about 60 kilometers burial depth. So this is pretty deep already. And that is getting fragmented. It's getting fractured and modified here. So our working hypothesis is that could represent an earthquake event. So happening there at point 2 on the path. Later on, that's at about 80 kilometers depth. Going on even deeper, we see fluids have resorbed that garnet and grown a new composition, and then finally we end up coming back up again. So this is still work in progress. There are obviously lots of people working on this, but I think it's exciting and interesting to think that we have a new window in terms of thinking about some of these processes, and there's a lot of questions to be answered of how representative are these exhumed rocks compared to rocks that are going down a subduction zone like we have off of Cascadia, because of course in subduction zones like we have, most of the rocks by definition don't come back to the surface. So are these anomalous, or are these something that can give us some insight? So I think there's a lot of exciting questions to explore. So where next? I'm part of a group organizing an international conference this June. So we're bringing about 100 researchers from about 20 different countries, and it'll be really exciting to be in that environment, seeing the latest developments and charting where there's particular opportunities for some future progress. And you might notice one of the organizers is none other than David himself. He is now a faculty member at University of Illinois, Chicago. He was a master's student here just a few years ago, so that's really exciting to see him establishing his career there. But I'm not going to do deep dive on this. We're going to shift gears. We're going to follow the fluids, right? We've done our earthquake bit. What happens when those rise up? They're causing melting. They're ultimately going up into the mantle wedge and building our continents. So we're going to look at building continents in the North Cascades, following those fluids up to shallower depths. And this is, again, involved a lot of collaborators, a lot of students. So let's look at this. So North Cascades, crystalline core, many of you are familiar with this. It's not too far away from campus. It's just the tail end of this huge 1,500 kilometer long belt of the Coast Plutonic Complex, this magmatic arc. And what's exciting and interesting about this area is it's one of only about 9 localities in the world where we have these kind of deep levels of a magmatic arc exposed, where we can actually study them. And so that's really interesting. So just to remind you, we're pretty close to where Central is, really, just a little over a couple hours away. So here's a bit of an overview of features that we can see in the field. There's a lot going on with these rocks. So we can see here in this image that we have some of these mafic and even ultramafic compositions that are fractured apart, invaded by melts. And our interpretation is that this is early stage mafic magmas coming up into pre-existing crust, crystallizing, fully solidifying, but then getting disrupted by the later stages of this process, when everything became hot and ductile and mobile and even partially melting. There's others here where you can see more cross-cutting features. So we're getting a little bit more into igneous territory here, looking at fractional crystallization and assimilation processes, where these melts are interacting with those pre-existing rocks, digesting them, modifying their compositions. And so it's exciting to be able to see the field evidence and the relationships for these processes that we can infer from things that we see at the surface. So actually comparing our inferences to what we can actually see in rocks from those depths, and gives us insight of what's going on underneath the surface beneath the modern Cascades arc today. So in terms of how this project went, I had Megan Chelland, a master's student. Here she is collecting a sample. Had some undergrads assisting with this. There's Jared helping with this very detailed outcrop mapping. Again, it's getting thin sections, separating zircons for geochronology, which we'll talk a little bit more about. And Megan and Jared did an amazing job doing this detailed outcrop map. There's a lot going on here. And so they picked apart those different cross-cutting relationships. We got samples of those different components so we could put together this, this story of what's going on here. So to add time to that story, we turn to the mineral zircon. It's a tiny little mineral, little tiny sand grain sized things, maybe not familiar to everybody, but it is a really, really valuable tool in terms of high precision and robust geochronology when we're dealing with very complex rocks that have had a long and convoluted history. And you can see just in this image right here, this is an image taken on the scanning electron microscope, and you can see multiple different zones just in one grain. So you can see here's some zoning, it's cross-cut, it's truncated by another zone. You can see that both of those are cut by yet another zone, and then you can see there's even another one out at the rim. So we can start picking apart this complex history. And what's really exciting about the analytical techniques that we have nowadays is we're not just measuring ages. When we're dealing with these complex rocks, if we measure an age, well, great, what does it mean? And so a big part of my work that I didn't mention with the ultra-high pressure rocks was really addressing exactly that question and using trace elements and not just the isotopic information to pick that apart. And so here's a photo of the lab at UC Santa Barbara where we're using a laser to basically drill into these grains. These are little laser spots, and feed that signal into actually 2 different mass spectrometers. So we can get age information and trace element information rapidly and from the same spots. And so it gains us tremendous power in terms of making sense of what's going on. So just to give you a little bit of an idea here, so I showed you before the earlier stages of that process. There's an image showing what those minerals look like when they're separated out. We mount them up, we image them, and then analyze them. And here's a photo from a few years ago. My collaborators Erin Shea and her master's student Alex Busk physically at the lab. One thing, again, the cool ways that technological advances can make our work more productive. So my student Carla Ortega, who will be featured a little bit later, she was able to connect these analyses using the same lab from her office, operating this instrument remotely. So that saved us a lot of time and a lot of money, not having to physically travel down there the way we've had to do in the past. So we can see here multiple different age zones. Some of them we can know that they're different even though the ages don't have a difference. Here it's about 112, and here it's also about 112, but the textures and also the trace elements tell us these are recording different parts of the rock's history. And if we summarize that, here, I apologize, this is a little bit of a busy plot, but it's a lot of data. So on the y-axis, we have the age of each analysis in millions of years, and every little black bar represents an age, and the size of the bar represents its uncertainty. And so what you can see is there's a broad range of ages represented, but there are some age populations which are quite prominent. So we can see here some old values up here in the Triassic, and a larger component here of Jurassic ages, so a lot in the 160s to 170 million years. So this is the pre-existing crust that was there before that migmatite complex started forming. And then the main action happens down here. So starting between about 110, 120 million years, we're really getting a lot of this process taking place. We see a big spike here right at about 100 million years, which is very interesting because that lines up pretty well with a very major tectonic event that extends across the entire western US in terms of what its significance is, terrain accretion, or something else. That's people have different opinions about that, but the point is this is part of a much bigger story. And again, that's something I really find exciting. It's not just looking at something in isolation, but plugging into that bigger picture. And then finally, we see the system cooling down and coming to a close here between about 95 and 90 million years ago. Now, as part of this, there are lots of different facets, lots of different directions to go. But it was about this time that more and more students were expressing interest in economic geology. And so I thought, well, here's an opportunity that we have. I know there's sulfide minerals associated with these rocks. other than making note in passing, I'd never paid any attention to them. It's like, well, let's get a little student project. Let's have a look. So I had a couple of students, Colton Bell and Sam Ayasu, who worked on this. And here's an image collected on our scanning electron microscope upstairs here in this building. I would say that's another factor is before about 2016, we didn't have this building and the resources and the equipment that are here. And even though I collaborated with labs that had those type of capabilities, it's a very different animal if you can just go upstairs and explore an idea that you have, as opposed to you're scheduling months in advance and you're booking a certain number of days and you just have time to get through what you're planning to get through, and you don't really have the opportunity for that more exploratory research. And so this is something that we're really fortunate to have some of the facilities and resources that we have here, and I think it's really cool for all of you as students that you get to use them in classes. Obviously, I do that in my classes. I know Carrie does that a lot in her classes, and many other faculty too as well. And I think that's something to appreciate and reflect on, that not everybody has those opportunities. So this was a start here, so discovering these interesting textural relationships between chalcopyrite, so it's a copper iron sulfide mineral. It's one of the principal ore minerals for copper, and some interesting textural relationships. Sam and Colton presented at the COVID era GSA in Portland in 2021. Here they are with their poster. We took some additional X-ray maps, and one thing that was really quite interesting to see is over here on the bottom left side of the screen, this is cobalt. So this is a mineral, an element that you might have heard of. This is one of the so-called critical minerals, especially for high-performance battery technology, that is actually the single rarest element in the Earth's crust, and is in very limited supply. So that was really interesting to start to see, hey, we know that people have these ideas that there's a lot of processes in the deep crust that are responsible for what ultimately forms an ore deposit up at shallower levels. And here was an opportunity to build on all that work that we had done. However, also at this time, a new opportunity arose. And that leads us then to chapter 3 of this, following the fluids part 3, critical mineral resources. So we started a partnership with Washington Geological Survey a few years ago. This has been really fabulous for our department. I'm really excited to have Andrew Sadowski here stationed with our department, and to have been able to have collaborations with WGS colleagues. And so actually all of my most recent students, basically the last 5 years, all of the master's projects have been collaborations with Washington Geological Survey. So that's been really exciting. So this got going here thanks initially to Alex Steele with the WGS. I reached out to him when I heard about the Earth MRI program and the WGS's involvement in it, and asked if there could be some possibility for us to collaborate. And so in 2022, I was able to go out in the field with Alex and Katie Alexander from WGS, and David Miller, new grad student at the time, was also able to come out. That was just before his start for his master's, and we were able to scope things out in the field and realize, wow, we've got some opportunities here. And so I pitched a couple of project ideas to Alex of ways that we could contribute with our resources and my expertise to contribute to their project. And that was to use pressure and temperature methods to say, where are we in the crust? How deep? What's our exposure level? Because that's an important parameter controlling the formation of an ore deposit. Different types of deposits tend to form at different levels of the crust. And geochronology of complex rocks is another thing that I specialize in, and in particular, being able to apply zircon, but with a different angle than I was showing you before that we'll get into. And so this has then since grown. So Carla, I'll share some of her data. Emily, who started this year, is going to be looking at another angle of this. Here's Davey and Dakota. And just as I was up here and I saw Gabe walk in the room, I realized in my haste of putting this together, I completely forgot to select my favorite photo of Gabe in his gigantic sombrero to add. So Gabe, I apologize for the oversight, but he's also been involved in this research. So how did I get here? I was not interested originally in economic geology. I did not have any exposure to it as an undergrad. There were no faculty members involved in it. so I didn't really know squat about it. The only thing that I had were some negative impressions, actually. I thought it's like, well, it's kind of an industry in decline, and I think mining, I think like pollution, and not a very nice thing. So I didn't think that was anything I was remotely interested in. And so my first inkling that there was more to it than that was when I was a graduate student in 2003, and there was an opportunity to go on an economic geology field trip to Yarrington, Nevada, and that was led by Dr. Marco Einaudi here, who actually did a lot of work out there before becoming a faculty member, made a lot of contributions in the field, and it was a really interesting and diverse group as well. So there was a small group of us from Stanford, none of whom actually were economic geologists, none of the students were, but we were there with a group of Peruvian geologists from the Yanacocha mining company. These were professional geologists coming there. It was really fabulous interacting with them and learning from them. And there were also some students and faculty from Colorado School of Mines and University of Arizona. And so we'd be out in the field during the day making observations. At night in the hotel room, Jeff Hedenquist, one of the Colorado School of Mines professors, would get this little compact digital projector and project up on the screen some of the photos from the day and do little mini evening lectures. And wow, I learned a ton. Before, I would have looked at these rocks and thought, well, they're kind of grungy and altered, but not really anything to see here. And then realized, no, there's actually a whole world in there. So that was really an eye-opener for me. But at that time, that wasn't a path that I was going down. But I filed away in the back of my mind. And so fast forward to now. Why is this important now? I feel this is the most exciting opportunity for geology in the last several decades. And geology and its importance is really in the public consciousness in a way that it has not been for many years, for the reason that there's been a confluence of events. One is there's a rapid growth in clean energy and other advanced technologies that, compared to older technologies, are far more mineral intensive but less energy intensive. So there's a trade-off. We're not using as much energy, but we are needing much more of a supply of mineral resources. And those mineral resource needs have really extended all the way across the entire periodic table. So unlike many decades ago where there were just a fairly short list of major commodity elements that were of interest, now it's a much more diverse bunch. And so that means there's a large increase in demand. And I think what's exciting is the idea of transitioning away from this energy-intensive set of technologies to a new set, which again is mineral intensive, but with a difference. This is not consumptive use of these minerals. Once they are part of our chain of technologies, there's a tremendous opportunity for recycling, and so that we can move our way towards a more circular economy where we're producing what we need from new raw materials, but then reusing what we have rather than just consuming it. And so I feel that's a really exciting transition. Combined with that, as you probably know, major supply chain disruptions with COVID. Geopolitical landscape is not looking fantastic in recent years, and that doesn't seem likely to change. And I think there's also a lot more awareness of the environmental and human rights angles, that the old idea of just do it in somebody else's backyard isn't really a great way to go, and that all is pointing towards the need for looking carefully at domestic mineral resources here. And we need people to do that and develop it in a responsible way that is beneficial to the communities there, that doesn't leave a mess of the environment, and there are ways to do it. But the workforce basically is a key bottleneck. This is an area that has not really seen major investment in at least 30 years. And there's a real need, and there's a need for that to develop quite rapidly. So I think it's a very exciting time for you as students, because there are a lot of opportunities out there. And I think it's also important to know that there's opportunities in a lot of different career paths. So if you love the field, great. There's a lot of need for that, but maybe that's not your cup of tea. Laboratory methods, advanced laboratory methods, are also a key skill. We also need people who can do things on the computational side. And again, thinking about collaborating, bringing together those different skill sets to help solve these bigger challenges. So where does this leave us in terms of Washington? So this is some information off of the WGS Geology portal. I imagine many of you are familiar with this. There's loads of great information on there. All these little symbols that are plotted on top of Washington's geology are localities of historically explored or developed mineral deposits. As you can see, there's a lot. The other thing that you can see is very many of these correlate with occurrences of metamorphic rocks and related plutonic rocks. So the deeper processes of Earth's interior is really key to understanding why are these deposits occurring where they are? How can we use that to more intelligently think about how we might responsibly develop more of these resources? The other thing I think is really cool is Washington's tectonic history and terrain accretion is also a key part of this story. So again, for me, it scratches that itch of plugging things into a bigger picture. This is not just drilling down in your little silo doing one thing, but it's contributing to a specific need, but it's also contributing to our bigger picture understanding, and really integrates a lot of different types of information, which I find very exciting. So where's the funding coming from this? It's coming from the Earth MRI program from the USGS, who is funding Washington Geological Survey, who is very generously collaborating with us to support our work in this. So the goal of Earth MRI is generating and updating geologic maps and gathering new data relevant to mineral resources. And so northeastern Washington is a focus. As you could see from that previous map, there are a lot of mineral localities there. This map here is a mineral systems favorability model. And one of the things I think is cool is they're taking a mineral systems approach. So unlike in the old days where you were focused on one commodity, we're after copper or we're after gold, but actually looking at it more holistically, thinking about what elements geochemically are going to occur together and what other resources are there that are associated with these. Because again, decades in the past, people weren't interested in most of the periodic table, for one. The technology was not very good or efficient. So there's also a lot of mine wastes that are out there on the landscape that represent a very important mineral resource. And the mineralogy and the petrology and the textures of those are really important in terms of thinking of those as a potential resource as well. This is not all about digging brand new stuff out of the ground. It's also about making wise use of stuff that's already been done in the past. So I think that mineral systems approach is really exciting. One element of particular interest here is tungsten. That's not top line of your critical minerals list that you might be familiar with, but it does have some really interesting applications. So particularly as a catalyst for things like fuel cells, green chemistry, where you're basically using catalytic properties of a catalyst as a substitute for energy-intensive high-temperature processes that are traditionally used. It's also used in microchips, superalloys for aerospace applications, especially high efficiency, jet engines, of course manufacturing, medical imaging, lots of different things, even though it's not maybe one of the ones you've heard about in the news. So what I'm going to show next is a lot of the master's projects of David Miller and Robin Gaudet and Carla Ortega. So this is a slide that I've adapted from David's defense talk that some of you might have seen just last spring. So we're looking at a couple of areas. Sorry, I should actually go back there. These two field areas up here, the Adams Mountain Hunter Quad right here and the Orient Quad up here in the north are the two areas we're going to zoom in on. So going first to Adams Mountain and Hunters, again, this is an area with multiple historic mining activities, a broad range of different elements, many of which are on that critical elements list. And here's a photo here showing some of that tungsten ore, the mineral wolframite. I'm sure that's on your everyday list. It certainly was a new one for me to learn. So it's an iron manganese tungstate mineral. And let me walk you through this diagram. One of the things we're doing is, in addition to ages, is again using those trace elements. And one thing that I learned about, again, as part of my work on ultra-high pressure rocks, is that oxidation state was something that zircon trace elements could help us tell. And that has really blossomed over the last 20 years since I first learned about it. And so why is that important? So I love Carla's little illustration here of the avocado. So we have a low oxidation state. We have our nice green avocado. If our avocado has been exposed to oxygen in the air, it turns brown. So minerals are kind of the same thing. They're going to have their preferred happy place in terms of the amount of oxygen for them to be able to form. So this is an important factor that can influence what type of elements get concentrated. And so what we found from that research is here is temperature determined from the zircon versus oxidation state. So don't worry about these numbers so much. Oxidized at the top, reduced at the bottom. All the green and purple and blue symbols, those are associated with tungsten mineralization happening in the mid-Cretaceous, whereas the orange and red symbols are not, and they're younger, and we see they're more oxidized and higher temperature. So we're seeing some clear differences, and again, the ability to use this as one tool for helping us understand how these things form, how do we explore for them. Another angle, here applying some machine learning techniques to do some quantitative phase analysis to improve our pressure and temperature constraints. So just a couple of examples here from David's thesis. So some of these non-mineralized plutons in the 70-ish MA range are quite shallow, whereas some of the areas up in the Orient Quad, where we're focusing our more recent work, came from quite deep, 20 or 30 kilometers depth. So a really big difference in crustal exposure level that we can determine from this modeling. Some of the more hot off the press data, this is from Carla's work. One big difference up north, we have a very voluminous Eocene magmatic story, which we don't see down in the south. And what's really fascinating, this is coming out a lot of magma and very fast. So within 600,000 years or so, we're generating a lot of these plutons. So that is very interesting. There's a lot going on in the Eocene, as I'm sure many of you know. And here, just doing a comparison. This is a slightly different style of plot, but again, similar information. And what we see here, those samples from up north that are Eocene, those are the purple stars, generally higher temperature, more oxidized. They look more similar to worldwide comparisons to things like copper deposits. Here are a couple examples from China. Whereas those Cretaceous samples associated with the tungsten mineralization in the Adams Mountain Hunters quadrangles to the south, more reduced and lower temperature, and also generally more similar to here a tungsten deposit from China. So again, I think this is a tool that will be really valuable. Zircon is great because it's very robust to hydrothermal alteration, and a lot of times there's a lot of hydrothermal fluids, remember the fluids, there, which means a lot of other ways of recording this information will get obliterated by later processes. So to wrap up, I wanted to just put this out to any of you in the audience who might have information that could help us with this. This is an ongoing research project, but it turns out there's actually very little information available from some of the previous exploration activity. And so here's just a few examples. I kind of like this. It's a little bit funny here. It's from 1947, this ad trying to attract investors in, obviously without evident success because they stopped the operation not long after that. But one of these localities, the Talisman Mine, is one of these tungsten localities that we're interested in studying. And here is a little snip from 1991 talking about some exploration work. But again, a lot of this stuff, maybe it's proprietary, maybe it no longer exists, but if there's any information that could be shared, it would really be valuable for us to help put our work in context. Or maybe some of you out there know, have some photos or just some history about these. And if you do, that would be wonderful if you could get in touch. So thanks so much for your attention. And again, my contact there if you have any tips, and I'd be happy to take questions.
Thank you, Chris. We have some time for questions, and Chris will repeat your question for the home crowd as well. Who's got some questions?
Yeah, Isabella. Sorry, could you repeat that? Oh, buffer curves. Okay, we've got somebody who actually knows about this stuff. Let me go back here.
What's the
So
question, Chris?
the question is, what buffer curves did we use? So let me explain what that even is. Just in interest of time, I've just sort of ignored the axis here. That's not really good practice generally. But when we're talking about oxidation state, there are a few different ways we can measure that. So typically, when you're dealing with higher temperature systems, there's something called oxygen fugacity, which is basically the thermodynamically effective amount of oxygen that's available to react. And that's what those numbers are there on that y-axis. But it turns out, really what's more useful is to think about how does that compare to mineral reactions that would happen in real rocks. And so to do that, we compare to what are referred to as buffer curves. And so there's a couple. That's with these dotted lines here. And so what you notice is this increases dramatically as a function of temperature. So this one right here, for example, is labeled FMQ. So what is that? It's the reaction between phthalate, which is the iron end member of olivine, so iron 2+ in a silicate mineral. If you add oxygen, the iron can oxidize and form magnetite, so that contains both iron 2 and iron 3+. It's, as probably many of you have seen, those little black octahedral shaped minerals. It's magnetic, right? It's more oxidized, plus silica. So we can think about where does that reaction take place as a function of temperature and the amount of oxygen, because that is much more representative of those types of oxidation or reduction reactions that are taking place in real rocks. So yeah, thank you for that question. I realize I just breezed right past that. Carrie. Okay, water-rock interaction, what's going on, and has anyone done any stable isotopes? I don't know if anyone has done any stable isotopes. In terms of the water-rock interaction, this is something that I think we'll be getting into more as part of Emily Stivison's master's project, where we're really looking more specifically at the mineral assemblages and mineral textures there and starting to think about what's going on. What has really impressed me so far is what a tremendous variety of different types of mineral deposits there are up there. Kind of every one we look at is almost a different story. So for example, one of the places that we're looking at is referred to as the Big Iron Deposit. It's a massive amount of magnetite. And it seems like their highly saline fluids are the preferred mechanism for transporting that, just as one example. But clearly, the fluids are playing a very important role, and we're just starting to dig into that. And for me, a lot of this, again, because I'm not an economic geologist, and this is not my background, is learning more about that, collaborating with other people who are more knowledgeable. And so yeah, if you have any particular ideas about how, say, stable isotopes or other techniques might be helpful, that would be great to talk more about. Let's see, Rebecca, I think you had a question?
Yeah, actually, in the program that you're working on now, do you see a lot of forward movement towards some of the interactions between the renewable technologies and the minerals as a part of additional study opportunities in the future?
Okay, as connections between the renewable energy industry and the minerals. So I haven't directly been involved with that, but I do know that's been a major shift in perspective of kind of historically the tendency was mining companies produce the metals, they go onto some metals market, and if you're a manufacturer who's producing some piece of technology that uses those, you just buy them on the international market and you don't really think twice about it. You know, electricity comes out of the wall and water comes out of the tap, and why should, right? That's how the world works, isn't it? But because of the constricted supply chain, there is definitely a lot more interest in the more major manufacturers actually working more directly with other parts of the supply chain. So for us, this is very, we're involved in the very foundational level stuff, so there's not like the imminent prospect of mineral production coming from these localities. This is kind of broader picture, setting the context and doing the more high risk and exploratory work that might set the groundwork for that. So that is not something I've had the opportunity to be part of yet, but I think it's really exciting.
I have one. I didn't realize you were collaborating so closely with the Washington Geological Survey. So did you approach them with this economic geology angle, and are you going to continue to create some opportunities from some of our students?
Oh, yeah. Well, so the history on that, I think it was about 2018 perhaps or so that Dave Norman, who was the chief geologist of Washington State at the time, reached out. And this was an idea he had had for some while, that WGS years past had a presence in the eastern part of the state, I think more in the Spokane region. But really for the last 20 plus years, they'd been entirely based on the west side out of Olympia. Obviously that's where the major population centers are. There's a ton to do over there. But he saw that there was a need to, again, connect what's going on both sides of the Cascades. And so that's how we set up that partnership, which led to Andrew being stationed with our department. And so when that happened, one thing that I felt was really important is that we grow and nurture that partnership and seek out opportunities for collaborative research. And it's been fantastic. I mean, many of our students have gotten jobs with WGS. It's been fantastic for me. So my first project was actually something I didn't even talk about at all, which is more related to our local earthquake hazard. So I had my student, Zach Stevens, collaborating with Megan Anderson with the geophysics team. And one thing I think is really cool about WGS is they're integrating the surface geologic mapping with the geophysical techniques to produce that more comprehensive 3D view into the Earth. But one of the needed ingredients is you need to know the density and you need to know the magnetic properties of the units that might be down there. And so I realized this was an opportunity where I could use my expertise of picking those samples that could give us that information, right? You want something that's representative of what's at depth. You don't want it to be swamped out by later alteration processes happening at the surface. And so that was really interesting and actually led to a significant revision of some of their modeling, because we had some different values and also led to some new insights. And then after that, I learned, again, because of this partnership, I participate in the annual state map meetings, advisory meetings, and that's how I learned about the Earth MRI program and that WGS was getting involved. And so I reached out to Alex and asked about opportunities, and we went from there. So yeah, this is absolutely something that I would like to keep doing and continuing. I feel it's really exciting to be collaborating with the WGS folks, getting students exposure to work with a state agency, contributing to this urgent problem. And again, because it's been an area that's not been invested in for so many years, I feel it's not something where you just leave it only to the people who have that specific training and expertise. I kind of feel all of us who have something to contribute should be contributing where we can. And again, it's been really exciting. I've learned a lot. I continue to learn a lot, and I think it's been really exciting for our students as well.
Excellent. Thank you, Chris. Hey, let's thank Chris one more time for a great talk. If you still have a few questions, come on up and talk to the man himself. Otherwise, we'll see you next Friday. Have a good weekend. Goodbye. 304 people. Go talk to Tim Melbourne. He's desperate. Excellent talk.
Okay. Well, thank you, Nick.
Oh my gosh, Chris. I'm going to take the mic from you here.
Thank you.
You can deal with your adoring fans, but you are a pro. Well, thank you, everybody, for joining us today. Oh, hang on.
Well, that would be great.
Slip by you here, see.
Knowledge, but knowing who the right people are and knowing.
Well, thank you, everybody, for joining us today. I hope you enjoyed that talk. Boy, I sure thought that was a great one. That's just my opinion, though, I guess. There's Hannah Shamloo talking to two of her undergrads who are now working with her intimately in the lab. It's wonderful to see that. Let's give them some privacy. Very good. What's the schedule? If you're new to us here, you're welcome to come back. We do these Fridays at noon here in Pacific time zone. And next week is February 7th, and a former student here, Sean Scott, will be making a triumphant return. And he's working down in Tri-Cities, Washington at the Pacific Northwest National Laboratory, the PNNL. And he'll be doing something on nuclear forensics. I have no idea what that means, but you probably do. And Sean is hoping to create some collaborations between PNNL and CWU Geology. So we are intentional these days. We are intentional about making very close connections with certain laboratories and certain state agencies, like the Washington Geological Survey that Chris Mattinson was talking about today, based out of Olympia. We have Andrew Sadowski, who is a full-time employee for the WGS. Jordan Carey, who is starting to develop a relationship with WGS and CWU. And then the PNNL. So to this point, and I've been here a long time, it's always been kind of a casual thing. The good students, we kind of create opportunities for them, and you should go talk to that person. Maybe you can get an internship. Well, we're trying to do more than that now for a number of reasons. And we'll take Valentine's Day off, and then we'll be back for 2 more talks in late February. Ann Egger talking about science education, and Paul Winberry talking about geophysics with the Antarctic ice sheet. Okay, thank you very much, everybody. I love you, and thank you for joining us today. We'll see some of you tomorrow morning, 8 a.m. Pacific time, from my office for Big Red Plutons, episode S. Thank you. I love you and goodbye from Ellensburg, Washington, USA.